All right, so hi, my name is Mikola Lysenko. I'm a graduate student at the University of Wisconsin in Madison. I have a blog, zerofps.net, which has a bunch of sort of side projects, and you can find me on GitHub and Twitter over there. But yeah, so what I'm going to talk about today is relativity, but in particular as it applies to video games. So, there we go. So, all right, video games on the web. Well, I would say that today we definitely have the technology. So we have things like WebSockets, which would be a more traditional thing, WebRTC, WebGL, WebAudio, this Gamepad API, and Node.js for building servers. So you would think that there should be this mass migration to the web as a platform because it's so much easier to get things installed and up and running and shared, and just onboard people into games. So where are the JavaScript games? Who's building this stuff? And in particular, who are building the multiplayer games? Because these are, the ones which are going to be the most engaging and fun and kind of technically interesting to try doing, right? So what's happening with this, right? So looking around, and I've tried this a couple of times myself, making various things for 48-hour, game programming competitions and other events, that online multiplayer games are just really hard because you basically have all of the classically difficult problems of game programming, so you have to deal with graphics and physics and low latency requirements, and then combine that with all of the complexity that comes with distributed and decentralized systems. So, this shouldn't be too much of a surprise, but it's maybe a perspective which is not frequently adopted, that multiplayer games are essentially distributed replicas. So you have many different machines which all have one common state, and you want to basically replicate that state as all the players are updating it locally to all of the other clients in the network, and do this in, say, less than 15 milliseconds, per frame, so that you can get this going, really quick. Unfortunately, distributed systems programming is really hard, and because multiplayer games are basically distributed systems, there are a couple of problems that are unique to multiplayer games in particular, which really are just general distributed systems problems. So we see the sort of issue of Byzantine failures because you can just have arbitrary problems in a network as a decentralized system. And we also have new types of resources that we need to worry about conserving and budgeting in a multiplayer game. So we have to worry about bandwidth constraints and latency requirements, which come from round-trip messages over a network. And in the case of games, these are somewhat acknowledged, but they're usually referred to as different types of things. So Byzantine failures in a decentralized system really just turn into cheating in video games. And this is just because players are kind of jerks, and they'll always try to do something, to break your game, And so there are a couple of solutions. The easiest one, and the one you see most frequently, is you just create one master replica, and then everyone just copies what that guy does, and don't think too hard about trying to validate all the other inputs. You can trust the central authority; they control the whole story. This has some kind of bonuses to it, cynically speaking, right? Because if there is one server, then you can actually own that server because it's now the one way to play the game, and you can charge an admission fee in order to get people into the game. So there are some, maybe business reasons that you might actually prefer a client-server model as opposed to something more distributed. There are better solutions, though, through things like WebRTC and other different types of protocols for ensuring failures. But this is not actually the focus of this talk. I simply want to draw some attention to the issue. Instead, we're going to be talking more about the sort of problem of just doing the replication at a basic level. And so here we will become concerned with the resources that we would need to optimize in order to do this efficiently. So of these two resources, the simpler one to understand is bandwidth constraints. And this is the one equation I'm going to put on this slide, which is basically how we estimate or basically calculate a bandwidth and the bandwidth consumption in a multiplayer game. So we have this variable b here, which we're going to let stand for the amount of bandwidth that we're consuming in, say, bits per second. And this will basically be proportional to an input rate, which is going to be the size of a message times number of messages per second, right? And so this is going to basically vary as a function of how fast the players are tapping the buttons on their keyboard. times the total number of players squared. And the reason it's the number of players squared is because whenever any player does some update to the state, it has to propagate to all other players in the network. So you have basically this quadratic scaling factor in your system, which is sort of inherent if every player needs to see exactly the same game at the same time. So there's an easy solution here, which is you can just assume that n is small enough that it doesn't matter. So i.e. don't make a massively multiplayer online game. And then there are harder solutions. So you could try to maybe chop the players into tinier groups so then the quadratic factor becomes not so bad. Or you can do stuff like throttle the rate, so you lower the constant k as the number of players gets larger so that time runs slower, and try to do this in some adaptive way. Again, this is not a hard problem. Our solution is we'll just do the easy thing for now. We'll pretend n is small. So this leaves us with the last part of multiplayer games, which is lag. And this is when you can't just sweep under the rug. And it's a consequence of physics. It's a consequence of distributed systems. So whenever you're dealing with things that are at different physical locations, you have networking delays. There's nothing you can do to get rid of it. So the only easy solution to this is you just don't make a multiplayer game. That's it, right? Well, that's not an option for us. We're going to do multiplayer. So that's the topic of what I'm going to talk about today. So what are some of the different trade-offs? Well, it really comes down to how you want to think about consistency. So from a database perspective, the way that you would think about replicating operations on the database depend on the model of data consistency that you're going to assume. So if you can have fairly strong consistency algorithms, which would be sort of like your ACID or strict serializability for basically synchronizing all events inside your game, right? And if you do things in this order, then you're going to end up having to do a lot more coordination, and then there will be higher latency involved with each operation that a player chooses to take. The other extreme is you can make an extremely weak consistency model. So this would be kind of like an eventual consistency type of approach where writes just propagate freely and they all move from one node to another, and who cares? Maybe things will work at the end and maybe you'll have a problem, but just don't worry about it. Just free no synchronization whatsoever. And the advantage to that is that it's going to be really fast because you don't have to coordinate between two different nodes. They just push messages out onto the network and it just pops out at other places. So this is kind of like the sort of dichotomy that you usually see. And it's actually a spectrum because there's a lot of spaces in the middle, which we'll come to in a moment. So for now, let's sort of drill down into the easy solution, right? Which is just strict linearizability, i.e. lockstep synchronization. So in this model, basically what you have to do at the end of the day is have every player talk to every other player in the network somehow. So they all broadcast messages to one another, synchronize at a barrier, right? So that they're all now coordinated. Then broadcast the next array of messages, resynchronize, and just keep doing this. So you have this game state. In order to go take the next tick or time quantum, you have to communicate with everyone in the world, stop everything that's going on, and then you can take a step and then just keep redoing this. So this has got some advantages and disadvantages, right? So the nice thing is that, well, this is pretty much what you would see if you were writing things on a local system. So it looks exactly like there was no distributed system at all. And all your players are going to see the same ordering of events as they transpire, which is pretty nice. So you don't have to worry about any kind of weird things that could happen on that level. But the disadvantage is that your lag from when you push a button to when something happens in the game is going to be greater than or equal to the slowest round trip time in your entire network, which is pretty bad. So it's probably a no-go for most games other than really simple board game type things that are not really real time, so to speak. And it's also kind of annoying to do this if you don't actually replicate the whole state, but you just replicate the input events, because you can run into sort of bugs where maybe one client doesn't do things quite right and then they desynchronize, and then so not even malicious Byzantine failures, but just accidental Byzantine failures happen very frequently here, and it's much more fragile than even just the simple approach to do it. So this is sort of the naive way to do it. If you have a fast network connection, you just throw enough money at that problem, you can kind of make it go away. But you really can't use this most of the time. It's not good enough. So instead, what most games use is something more akin to eventual consistency, i.e. dead reckoning is what it's called. And this is based on sort of some military terminology. The idea is that you get inputs from players, you just apply them immediately as you would do that. Then you extrapolate to predict what would happen in the future. Now, of course, this doesn't really work, right? Because you're going to get other events that are going to contradict it. So then you have to do some, fancy footwork under the scenes and correct it and make it all work under the hood. And it's kind of a hack or whatever. You have to do like some weird stuff, shuffling things around, but you can make it work. So here's kind of a picture, as an illustration. So imagine you're doing sort of like lockstep synchronization, and this is from the perspective of the blue player watching the red player walk through some corridor over there, a little, serpentine pathway. And so if we were doing lockstep synchronization, or if there was no input lag whatsoever, so they were basically like in the same physical machine, then you might see something like this, where basically, the red player walks through the corridor, nothing interesting happens. Okay, so what if we, basically have some delay now added to the system? So we'll basically apply the events from the red player and then just keep extrapolating outward as they would move through the corridor, right? And the problem that you run into is because there is a delay from when the red player takes the corner to when they actually, get the message over to the blue player, we see this sort of snapping around and the red player slides through walls and like you just have, weird things like, that are obviously wrong and somewhat broken. So what many games do, and this is sort of the state of the art, is you just apply some sort of weird smoothing effect, like you put a spring force that damps the thing to the correct position. So instead of just teleporting there or snapping through a wall, you do some pseudo-physical correction force that makes them maybe more smoothly walk along the path. And within some parameters, and if you tweak it carefully enough, you can make it work. And this is, we have multiplayer games today, and this is a viable approach, in the sort of like limit of like developer effort and time, right? So this is like very much not an automatic thing, And more importantly, there are limits even to what you can do with these correction models. So if you really just turn the lag high enough, eventually these things are just going to fail too. So, you're using the same correction model, but just double the lag, and now he's like snapping through the walls again. So this is, a no-brainer that it's, not going to work perfectly, right? So this is the, dead reckoning approach. The big advantage is that it kills the lag, right? Because you push a button, stuff happens right away. Great. Disadvantage is it doesn't always work. This correction step is generally pretty expensive. And it is actually really hard to implement it. So you're going to have to basically maintain 3 versions of your game if you're going to do dead reckoning. First, you have the actual logic for your game, which tells you how you respond to inputs and then move things around. Then you have to like implement this sort of correction response, right, that snaps them there. And then you have to do this like other sort of like prediction layer on top of it. So you have like 3 parallel implementations of basically the same code path, which is like really, really painful to keep in sync. And so many multiplayer games ship with lots of bugs, and once you add multiplayer development and adding new features becomes really expensive because you have to keep these 3 chunks of code in like synchronization. So it's bad, and you get all kinds of visual glitches too. So okay, so what I'm up here to talk about though is not to just give you all doom and gloom, but maybe provide some more constructive alternatives. And this is probably the alternative to strong or weak consistency. So from distributed systems, we know that we have sort of strict, serializability on one perspective. And then on the other hand, we have like, fully commutative weak consistency. But there's this place in the middle, of causal consistency, which is sort of the optimal model of consistency. So causal consistency is as weak as you can possibly make it, right? But no weaker. And the basic idea is that you're only going to enforce some ordering on events if there is some logical connection between one or another. So the basic idea is similar to dead reckoning, except instead of just processing inputs in any order, we process the inputs in causal order. And so the result is that the local player can execute events sooner at a more recent point in time, and remote players can execute events farther back, so in the remote past. So they will maybe be running at some point in earlier time or earlier history. So here's sort of an idea of how this could perhaps sort of work. So if we imagine if we have 2 independent players, the left screen would be from the perspective of the red player, the right screen from the perspective of the blue player. then these two orderings of events would actually seem pretty reasonable. So the red player can shoot a bullet, first, or the blue player could shoot a bullet first. And since these aren't interacting, either ordering would be perfectly fine for the purposes of most games because there's no interactions here. So these two inputs, in a sense, they can commute. So you could execute one before the other or the other before the second, and everything's fine. No problems there. The issue, though, is that when you have interactions or causal relations between events, then commuting them can cause problems. So, for example, here, again, we see from the left the perspective of the red player and the right the perspective of the blue player. The red player shoots some laser or something at the blue player, and it hits them, and so he's like, all right, great, I made the shot. Whereas the blue player, which is seeing events at some different point in time, believes that he's gotten completely behind the barrier and the shot totally missed and everything's fine. So one of these orderings cannot or has to be like correct, and the other one would have to be false, or it's impossible for these two things to both exist at the same point in time. And so generally the way games deal with this is you have a master replica, or your server, which is going to agree on some prescribed version of events, and if you happen to think that you shot a player but it missed, well, too bad, you just you suck at Counter-Strike. So give it another shot, right? That's your problem. So this is not great, and it's somewhat frustrating, and it would be great if we had some way to kind of get around it. But it can actually get even worse. So if we sort of carry this out to another step, so this is maybe a thing that players would get mad about, but it can actually just completely break your game if you implement this sort of consistency arbitrarily or badly. So here we could imagine maybe in one ordering of events, the player opens up a door and walks through it, whereas in another ordering of events, the player walks through a door and then it happens to open after they step through it. And now this just becomes not even physically plausible and breaks whatever semblance of immersion or sense that the game had to it in the first place. So that's no good, right? So okay, so how do we define causality? And now this is where the relativity comes into the picture. And so I originally wrote about this on my blog at some length, but this is the math-free version of it, so it should be more palatable. The basic idea behind relativistic causality is that we have to make a couple of assumptions about how our game works. And so this is where we kind of draw a distinction between maybe games as an application and distributed systems in general. So in games, we're going to assume that no object travels faster than the speed of light. So we're going to put an upper limit on how fast things can go. This means no instant hit weapons or super fast projectiles. There will be some upper bound on how fast things are allowed to move. We're also going to assume, for the sake of simplicity, that all of our objects are points. So they're just going to be a singleton, point mass, and their trajectories that they will trace out will be curves. And that all interactions between particles or objects occur at discrete points in space-time. So there's a single instant and location that describes the interaction between any two objects. And we'll also require that our space is flat. So we're not going to deal with any sort of curving or weird issues. So it's basically just a simple, flat space-time where objects and events interact as points. All right? If you want to see the mathematical formulation of this, you can look at my blog. I'll post the slides over there, right? So that's the kind of assumption or the physical model that we're going to use to derive causality. And what this leads us to is something like this, right? And so this is, again, where we can derive this notion of causality from relativity. So if you have a point in space-time or some particle moving along a world line, the only events that it can possibly influence are the events in its causal future, right? Which is basically in this forward light cone extending out from the particle. So this kind of picture is something you see a lot in physics. It's called a Minkowski diagram. The way to read it is that the vertical axis is time, and then the horizontal axis represents space. And so this curve here would basically represent the history that an object would travel, at some point moving through space. And the constraint that we have is that this curve can't be moving too fast, so there's a bound on the slope, which means that if we pick an event at the origin, which is this point O, then there are certain events which can be influenced by this curve. There are other events which could have influenced this curve. And then there is this whole alternate other space, which is outside of the particle's light cone, that is completely independent. And so events affecting the history of this particle can only happen in the past. And so these other things to the side, these space-like points relative to this point at the origin, can just be executed independently. So no problems there with this sort of thing. So this is the basic causal relation that we're going to use to define causal consistency. And it's how we're going to implement replication for video games, right? And it should be pointed out that the reason that this works is because there is a combination of geometry or space and time, right? Whereas, with things like maybe vector clocks or other sort of more discrete variables, you don't actually have like a spatial component going on. So we're basically amortizing the latency over space, to hint about it. So here's kind of like a picture of how event updates would look in a system like this. We can imagine we have a collection of objects, maybe they're players or remotes or whatever, and they're basically sending events to some server. So we'll pretend that the red player is maybe the local player here. And as events are sent into the system, we're basically going to update like our current view of the world. So we have these world lines, one for each particle. A new event comes in, we update the world line, move it forward in time, and we're going to just keep doing this, And we want to make sure that we process the events in the order of causality. So we don't do one event until, we have another event that like could proceed before it in the causal relation. So this gray area up here is basically the space of events that are unknown, and then the area below this horizon is basically the space of all things which are completely determined. So once we have some event that updates this, light cone for all of the particles, then we know everything below that event is just determined completely. So within this sort of, Minkowski diagram picture of events happening in our game, we can go back and think about those previous two models of consistency from the perspective of how they would try to synchronize the state, or where they would put a current instant in time. And so the way to think about what this really does is with the concept of a Kochi surface. So Kochi surfaces are in some sense a snapshot of the entire world at an instant. Right? So a Kochi surface represents time as observed from any particular node within the system, or from any player. This is basically the spatial analog of vector clocks, though it actually predates vector clocks by about like 20 or 30 years, because they were invented by Stephen Hawking. In fact, if you read like Lamport's original paper, like Kochi surfaces are essentially the physical basis for vector clocks. And the basic idea behind a Kochi surface is that it is some hypersurface in space-time, which cuts out some intersection with all of these curves. And it has this property that if you take any world line, which happens to obey these axioms that I described earlier, so i.e. it's not moving faster than light, then the intersection of the Kochi surface with any world line is unique. What this means is that you can take any system of particles and their trajectories, and then any Kochi surface, and there is a unique point in space-time assigned to each particle in the system. So from this perspective, we could draw a Kochi surface for what lockstep synchronization does. So the lockstep synchronization model is we just wait until there is no event in coordinate time that happened before the latest event, and then we can update our clock by just moving it forward there. So if the red player was like local, then the view that the red player would see would basically be this orange line far in the past, before like where they are right now. So this is somewhat slow. In dead reckoning, you just draw a line that passes right through the red particle at the most recent point in time. The downside to this, though, is that it crosses into this horizon, and so you end up with events that are completely unknown. So what's going on in that gray area where it intersects this line is not predictable, and so you have to do some crazy, like, artificial intelligence or statistical modeling or just some weird thing. Maybe it works, maybe it doesn't, who knows. So that would basically be the standard approach to it. And of course, you can make it work if you have a good model for that, right? But that's a lot of work. It's hard to do. So the approach that I'm discussing in this talk is we make this adaptive. So instead of using a flat curve, we're going to use a curvy thing, right? That'll basically track this surface of space-time maybe a little more accurately. So we're just going to use like a bent Kochi surface instead of like a flat line, because it doesn't have to be flat, right? It can just be whatever, So as long as it has this unique intersection property, which can be characterized geometrically. So this adaptive Kochi surface has some weird consequences, and one of them is you experience a certain amount of time dilation. So from the perspective of the red player, if we have like some communication delay between red and blue. And if he shoots a bullet at the blue player, then you observe that the bullet slows down as it approaches remote players. And similarly, a remote player would observe a bullet accelerating out from some other player that shoots one. So you see things slow down near remote players, as they're like heading toward them, and as they're heading away, they accelerate, right? And you can work out the consequences of this, and there's more math on my blog if you choose to do it. Right. So that's the basic idea. So how do we go about and implement all this stuff? Well, it turns out it's actually not so bad. We really just need to satisfy sort of 3 basic properties. So persistence, determinism, and a decoupled rendering step. So the idea is that we want to have a complete view of the history of the state of the game. It's no longer enough to just store one instant or snapshot of it. So every client is going to have like the total history of all events that have happened in the game from the beginning of time to the end. And we're going to require that events which happen in this game are deterministic, so you can't roll any dice, and this means that every player is basically executing some sort of continuous analog of a state machine on each of these particles. And we're going to also require that rendering this game is not locked to any particular frame rate. And the way that we basically will render it is we'll just pick a Kochi surface, intersect it with the world lines for all the particles, and then draw them on the screen at their locations. So that's the idea. The advantages are you get responsive local inputs, correct ordering of events in this causal sense. But there are some costs. So the first is that you can't remove all lag, so it's never going to be quite as responsive as you'll get with dead reckoning, because dead reckoning can just remove like all semblance of causality, right? Of course, this is the price you pay for not having glitches, is that you have to do some coordination. It's not as free as weak consistency. And the bigger one, though, is that in order to apply this to a game, your game has to actually obey the laws of special relativity. So this actually causes some very severe constraints. One of them is that you can't actually implement rigid body dynamics in a system like this, because rigid bodies actually, like a rigid constraint between 2 point masses, requires an instantaneous transmission of information. So you can't actually have stacking boxes, which is a form of rigid body dynamics, in a multiplayer game that does this sort of replication. So yeah, it's no good. You have to actually have things that really do move at the speed of light and actually obey all of these physical properties. So if you don't do that, it's no good. And there are some other weird glitches too. So one kind of problem with this is that a malicious player in the system could choose to basically defer their actions until they've seen what other remote players do. So the way that this would work is that you just artificially create a certain amount of lag. So the idea is that, well, I'm just going to not act until I've recovered all the inputs from all the other players, and then I'll say what I was going to do, right? So you can sort of cheat a bit. And this gives you an advantage because you get a faster reaction time. And the other players will actually still see a consistent ordering of events, right? It's just there's going to be this extra lag in the system, but they'll still view causal relations correctly. So what does that look like if you do that in practice? Bullet time. Right, so this was actually a bug that was discovered in this approach back in 2004, right? And this guy wrote this paper on it. It's pretty fun, right? So to try all this out, I made a demo. So here we go. I'm going to go spin it up on Node. And it's using WebSockets, and it may crash over the network here. So please be kind and gentle to it. We'll see if it's going to die immediately here. Oh, shit. It's not even connecting.
Your IP might have changed.
Oh, maybe that's what happened. No, still the same IP.
Also, what network are you on?
NodeConf EU. All right, well, I can kind of show you the local version of it anyway. I don't want to spend all my time sitting up here. Okay. Right, so here's kind of what this looks like. Make a new window here. Right, so here's kind of the idea. So you can sort of walk around and shoot bullets. And you can see on the screen down here, that's where the blue player is moving. So if I shoot, there's some lag in here. But I can also go into bullet time. And the other players don't see it. Whoa. So yeah, that basically works. There's a couple of neat things that you can do with this. So you can actually visualize the whole space-time history. And this takes like maybe a couple of seconds to run here, because it just rebuilds the bundle every time you connect. Oh yeah, so here we go. So this is basically like the history of all particles and their world lines going from the time t0 to now. So, just like a little WebGL thing running. So yeah, that's kind of the idea. Maybe later on, I'll put the GitHub repo up and people can like download this and play around with it, try it out. But yeah, that's the basic demo.
What's your IP?
192.168.4.106. I don't know why it's not working. 4.106. Oh. Oh, it does. Okay, cool. All right, wow. Yeah, so how do I get my mouse back? Here we go. You press Shift. So, yeah. So that's basically it. Like when you die, you just reload the page. It's not really very advanced. So, and this also probably has a couple of bugs in it because I made some like last-minute changes when I was on the plane, and I was somewhat jet-lagged at the point. But yeah, actually, when I die, it doesn't work so well. All right, anyway, let's kind of get this moving. All right, so that's the idea. Okay, get to the end. All right, yeah. So thanks for listening to all that. I have a blog that kind of explains the details of this crazy talk. I hope you all had a fun time. Is there any like extra moments here? I have like extra slides. I probably don't need to go through it though. So, no. I think maybe I can just say like a couple of words more on the limitations of this. So, obviously this all sounds great, but like really that relativity constraint is actually pretty killer because of this little result from physics called the no interaction theorem. Basically, if you have like multi-body dynamics with many particles, you can either have Lorentz invariance, which means that it'll obey the laws of special relativity, or you can satisfy Newton's third law, but you can't do both. And breaking Newton's third law is actually like pretty terrible because it means you don't have conservation of energy and things just go horribly, horribly wrong. So yes, in a capture the flag game, you can make a demo that works, but this is really like, I should point out that there are unsolved theoretical issues that need to be, this is why it's mad science, right? So there you go. All right, that's it.